In this work, we present an approach for estimating general 3D room layout from a single view by render and compare. Our novel framework combines machine learning and geometric reasoning to recover general 3D room layout from a single view. As shown in this example, our method recovers complex layout that is consistent with the scene in 3D. Very common assumption in room layout estimation is that all rooms are of cuboid shape. As this is often not the case in practice, we transition from such assumptions to general room layouts. Machine learning techniques have been successfully applied before for the task of estimating cuboid room layouts. Can we derive similar machine learning models for the task of general room layout estimation? One large concern is the lack of training data for the theoretical models. Existing datasets assume strong prior on the layout structure and are typically limited to cuboid layouts, or in case of panorama images to Manhattan layouts. Instead, we use machine learning to extract geometric cues from a single input view, which is followed by a powerful formalization of geometric reasoning. Therefore, our method does not require training data specific to general 3D room layout estimation problem, and yet we are able to recover a variety of layout settings that include occlusions between layout components, multiple ceiling levels, and non-Manhattan layouts. Given a single input view, consisting of color image and optionally sensor depth, we rely on state-of-the-art methods for plane detection and semantic segmentation to extract 3D geometric cues. From the color image, planar CNN extracts planes instance segmentation. Optionally, it predicts corresponding planes parameters and a depth map that are used in cases when sensor depth data is not available. DeepLab v3+ extracts semantic segmentation from the color image, providing semantic meaning to the detected planes. When combined, we are able to extract layout planes from a single view. More exactly, by overlapping detected planar regions and semantic regions corresponding to layout categories, that is, floor, wall, or ceiling, we filter the layout planes from the remaining detections. We obtain instant segmentation of layout planes that we will later use in our optimization procedure. When depth data is available, we extract accurate parameters for each of the layout planes from the 3D points within the planar region by relying on a Ransack procedure. When sensor depth data is not available, we use the direct outputs from planar CNN to obtain the plane parameters. By intersecting layout planes, we obtain important 3D geometric cues about candidate layout corners and edges. Intersections between layout planes define a set of candidate 3D polygons. We introduce a novel formalization that solves the problem of estimating the general layout from a given set of candidate polygons in our notation R0 as a constrained discrete optimization problem. By performing an exhaustive search on candidate polygons, our optimization finds the optimal subset of polygons, or in our notation R hat, that minimizes 2D and 3D discrepancies between the layout estimate and the underlying scene. At the same time, the constraints enforce the optimization procedure to find solution which partitions the input image I. The cost term for the optimization procedure is divided into 2D and 3D parts. We calculate the 3D cost by first rendering the estimated layout depth and then comparing it to the depth map of the input view. In words, this cost penalizes all locations in the image where estimated layout components are located in front of objects in the scene. We calculate the 2D cost by comparing the estimated layout polygons and the detected planar regions in the image. The optimal layout should maximize the overlap of its layout components with their corresponding planar regions and minimize the overlap between layout components and other planar regions of the layout. The initial layout estimate is inconsistent with the scene. Due to occlusions between layout components, very often some layout planes might be invisible in the image. Hence, as is the case in this example, because of the missing planes, the initial set of candidate polygons does not include all of the necessary polygons. We detect and deal with remaining inconsistencies in a render and compare refinement step. First, we render the initial layout estimate in 3D and compare it to the depth map of the input view, similarly as we do when calculating the 3D cost. Next, if discrepancy is high, we find an additional plane that passes through the line of largest discrepancy change and the camera center. Therefore, we obtain an additional plane that is not part of the layout but supports the calculation of the final layout estimate. By rerunning our optimization, we refine the layout estimate and, if necessary, iteratively repeat the procedure until the estimated layout becomes consistent with the underlying scene. The refined room layout is consistent with the underlying scene both in 2D and 3D. As previously mentioned, there were no available datasets for evaluating the quality of general room layout estimates. We present a novel Scanet layout dataset that provides 3D manual layout annotations for roughly 300 different views that were sampled from the Scanet dataset. The images include a large variety of different layout settings captured from the challenging viewpoints. Additionally, we introduce 5 metrics to evaluate the quality of layout estimate in 2D and 3D. We show some of the quantitative evaluations on our Scanet layout benchmark. To better understand the complexity of the dataset, we first benchmark the Hirzer et al. Method. Even though the method is the state-of-the-art in cuboid layout estimation, it clearly underperforms on our benchmark, as indicated by its intersection over union value. This is expected, as the method cannot deal with non-cuboid layouts. In contrast, our approach shows much higher values. The IOU and the RMSE values indicate that, for our method, the accuracy of depth measurement is crucial for recovering accurate layouts. Hence, when depth data from a depth sensor is available, the accuracy of recovered layouts notably increase for our approach. Our qualitative evaluations demonstrate that when wall edges are completely occluded, the method assuming cuboid layouts can easily fail even on cuboid scene, as shown in the first row. Our approach focuses on visible geometrical cues in the image and performs geometrical reasoning in 3D to recover much better estimates. Clearly, the example in the second row demonstrates that the cuboid methods cannot recover general layouts in the Scanet layout benchmark. Our experiments on the cuboid benchmark show that our approach performs comparably to the methods designed specifically for estimating the cuboid layouts. Furthermore, we show an example where our approach recovers layouts that fits better to the scene than the manual annotation. These examples demonstrate the most common failure cases. Our estimates are shown in green and the manual annotations are shown in blue. The first two failures are due to noisy outputs from plain RCNN and dplyr v3+ that lead to both false positive and to false negative layout planes. The third example shows a view where our render and compare refinement fails due to large noise in depth. We present additional qualitative results on our Scanet layout benchmark. Our approach is able to recover a variety of layout settings. We demonstrate that the recovered layouts are indeed consistent with the underlying scene. Thank you for your attention. Please visit us at our virtual poster session for more information.